The question of what is the universe expanding into, it's really difficult for humans to understand because there isn't anything outside the universe. All of these missions are investigating dark energy and trying to understand what exactly is dark energy and how is it causing the accelerating expansion of the universe.
Today, we are going to be discussing one of the most important and least understood mysteries of the universe, what Stephen Hawking called the missing link in cosmology, the nature of dark matter and dark energy. My name is Doug Barr, and it's my pleasure to welcome you all to the St. Alina Forum for Innovation and Creativity. As most of you know, we are an educational nonprofit with a mission to entertain, inform, and we hope inspire. We're here to talk about the profound question, what is the universe made of? Nobody at this point actually knows for sure, but what we do know is some of the best minds on the planet are engaged in the effort to find an answer. Two of them are with us today at the forum. Dr. Alina Kiessling is a JPL research scientist investigating dark matter and dark energy through weak lensing analysis of n-body simulations. If you don't know what that is, you're going to know at the end of this conversation. She is a member of Euclid and the Large Synoptic Survey Telescope Dark Energy Science Collaboration and was a consultant with the Wide Field Infrared Survey Telescope Science Definition Reports. Additionally, Alina was a co-leader of the development of the 2020 Airship NASA Centennial Challenge to develop stratospheric airships for potential use as the low-cost platforms for astrophysics and earth science missions. Kiessling earned her BS at La Trobe University in Australia and her Ph.D. in astrophysics at the University of Edinburgh in the UK. Dr. Jason Rhodes graduated from Valley High School in West Des Moines, Iowa. He earned his BS in physics from Harvey Mudd College in Claremont, California, and an MA and a Ph.D. in physics from Princeton University. After stints as a researcher at NASA's Goddard Space Flight Center and Caltech in Pasadena, he landed at NASA's Jet Propulsion Laboratory. His long list of projects and responsibilities include NASA's Nancy Grace Roman Space Telescope, the European Space Agency's Euclid mission, and the Vera Rubin Observatory's Legacy Survey of Space and Time. All of these are designed to study dark energy, the hypothesized cause of the universe's accelerated expansion. Besides being colleagues at NASA and the Jet Propulsion Laboratory, Alina and Jason are husband and wife. And now, if everybody's ready, let's all welcome Dr. Alina Kiessling and Dr. Jason Rhodes. Well, hi, Alina, and hi, Jason. Thank you guys so much for joining us today at the St. Alina Forum.
We're thrilled to be here. Thanks for inviting us.
Yeah, thank you. We're so happy to be here.
Oh, it's our pleasure. It's great. We have a lot to talk about, so we're going to jump right into this. But before we address some of the big questions like, what's the universe made of? I think we ought to warm up with maybe some a little bit smaller or easier questions, but that remains to be seen. We'll see how small and easy it is. Alina, I'm going to start with you. Can you tell us how finding something in a cave in Australia when you were a young woman or a girl ended up being a dinosaur bone, and that perhaps was instrumental in getting you interested in the sciences? Is that true? And how did you end up not a paleontologist, but rather an astrophysicist?
Right, you've done your research. So when I was a little girl in Australia with my family, we used to go camping every school holidays. We'd jump in my dad's big old Land Rover and we'd drive into the central desert of Australia. And we used to go to an old opal mining town. And while we were camping in this opal mining town, I was digging and looking for opals, and out fell this big rock, and it had opal on it. It was really exciting. And we looked more closely and we discovered that it was a dinosaur bone. And I was so excited, and it made me think about beginnings and origins, and it made me really want to understand the origin of the Earth. And so I thought I wanted to be a paleontologist. And then as I grew a little older, so I was about 7 years old at this time, and I went into high school, I realized that I was thinking far too small and that I actually wanted to understand the origins of the universe. And that's when my passion for cosmology began, and I pursued a career in astrophysics and cosmology and ultimately ended up here at NASA working on some fantastic missions that are exploring exactly that.
It is clearly a really exciting time in cosmology. It is so many different telescopes, so much is going on now, it's hard to even keep up with it. Jason, I know that when you were growing up in Iowa, you had nothing to do with opal mining in your background, because I grew up in Iowa as well, as you know, and so let me just ask you this. What I did have in Iowa, not opals, but I did have some great teachers in high school and even in grade school that were really inspirational to me, and they ended up being mentors. Did you discover your interest in science and then physics and astrophysics, any of that in Iowa, or did that all come later in your life?
Oh, I absolutely was interested in science and space and understanding the world around me from a very young age. And I think for me, the big inspiration was starting when I was able to read a lot of science and science fiction. And I interspersed reading science fiction with science fact from some great authors that have written in both areas, like Isaac Asimov and Carl Sagan. And I really enjoyed reading about science, learning about what we knew about the universe, and then reading these stories about the far or even near future about what science could be telling us or could bring us. And so I did a lot of reading and fell in love with the idea of understanding the universe through studying it.
That's fantastic. That's really great. You know, all scientists are, without question, people who have curiosity, deep curiosity, a driving curiosity. For you, it seems like your curiosity took you into the bigger picture of outer space and beyond. And is that pretty much what's driven your career and helped you choose the projects that you've chosen?
It is. And when I was thinking about going to college and then thinking about going to grad school after college, at that time, we thought the biggest component of the universe was this matter called dark matter that we'll talk a little bit about later. And I thought, okay, if this is the biggest component of the universe, I want to go understand this. And so that was what really drove me in my early academic career. But by the time I ended graduate school, we had found out that an even bigger component of the universe is something we call dark energy. So there was a new phenomena for me to explore as I began my early career after school.
That's fantastic. So you've both been hooked on this for quite a long time, the idea of dark energy and dark matter. Where did you meet before we finish these personal questions? Then we're going to get right into dark energy and dark matter. Where did you guys actually meet?
So I'll start the story and Jason can maybe follow it up. But when I was in early grad school in Australia, I was coming to a meeting here in the US, and I started looking at people who worked in a similar field to what I was interested in. And so I started emailing those people. Jason was one of them. And we arranged to meet at Caltech to talk about our science. And then as I progressed through my career, I went and finished off grad school at the University of Edinburgh. Jason and I stayed in touch, and then finally, when I finished grad school, I came and I started a postdoc here at NASA's Jet Propulsion Laboratory, and that whole time we'd remained friends.
Yeah, so we were friends when Alina started at JPL, and after about a year of Alina being at JPL, we had become best friends, and I said, you know what, maybe we should take this to the next level. And Alina's initial reaction was, no, we're perfect as friends. And then after a little while, she said, you know what, I think you're right. And the rest is history.
So dark energy in this case brought you together. It didn't send you out into space, separating you.
That's right.
So before we dive into the subject of dark energy and all that goes with it, I wonder if you could give us a little bit of background on how we, at this point, know the universe is expanding and how we know that the expansion is accelerating. And what I'm thinking of is, I think probably back in 8th grade, we all heard about the Big Bang Theory and the Belgian priest who who came up with the Big Bang idea, and then Edward Hubble, before that, even in 1929, came up with redshift calculations to prove that the universe is expanding. But then, now more recently, can you talk about the Planck telescope? Maybe, I don't know, maybe this is something you don't know about or aren't interested in, but I'm sure you probably do. The Planck telescope did a measurement, and this is what it was showing, that the universe is in fact expanding and accelerating in its expansion. And then there was a second measurement that was done by the Hubble Space Telescope, and then that was confirmed by the Webb. And that then showed that expansion is absolutely happening, but much more importantly, even is accelerating. And so can you just run through that? Did I get that right? And can you confirm what that is and what that was about?
All right, so let's talk about how we know the universe is expanding and how we know that expansion is accelerating. So almost 100 years ago, a pioneering astronomer named Edwin Hubble did some observations of at what was at that time distant galaxies. Now they'd be considered close by galaxies because we can look much further in the universe. But I'm sitting here in a TV studio at JPL, but if I was outside and I pointed just up here, you could see Mount Wilson where Hubble did these observations. It's just a few miles away from where we're sitting now. And what he found was that no matter what direction he looked, the farther away a galaxy was, the faster it was moving away from us. And what this told Hubble at the time was that the universe was expanding, because everywhere you look, everything's moving away. The further out you look, further back in time you're looking, and the faster things are expanding. And for a quarter or 3/4 of a century, astronomers thought, okay, the universe is expanding, but it's probably slowing down. Gravity's probably slowing down that expansion. And then in the late 90s, a number of astronomers did some studies to see how much that expansion was slowing down. And it was two groups that almost simultaneously found that expansion wasn't slowing down, it was accelerating. That is, over time, the expansion is getting faster and faster. And this was counterintuitive because you'd think gravity would slow down that expansion. And so we call whatever's causing that runaway expansion of the universe dark energy. And this model of the universe in which we have dark energy, dark matter, and normal matter, galaxies and stars, that's our standard model of the universe. And this standard model of the universe was pretty definitively shown to be at least very nearly correct by the magnificent Planck telescope that you mentioned, a European Space Agency telescope with a big NASA component to the technology of the telescope and the science that the telescope did. And then people were also measuring the expansion of the universe with both the Hubble and more recently the James Webb Space Telescope. And all of these measurements show that indeed we have an expanding universe that probably had a Big Bang about 13 billion years ago, and that expansion started somewhat slowly and has been accelerating, especially in the last half of the history of the universe.
Alina, I read a description you wrote about the size of the universe. You said 1 million Earths could fit into our sun. Our sun is obviously a star. In one galaxy, there are 100 billion stars. In the universe, there are over 100 billion galaxies. So there are 100 billion galaxies times 100 billion stars, which equals 10 billion trillion stars in the universe. This is the scale we're talking about here. It's almost impossible to put into a human brain, but that's the size of what we're talking about, and the history and the timing on it is also equally astonishing. But considering that scale, if we are expanding, won't that take a great deal, and accelerating the expansion, wouldn't it take a great deal of energy to create that acceleration? And where the hell is all that energy?
So the universe, we know, is accelerating in its expansion. And as you just mentioned, the universe is full of a huge amount of stuff. And the question of what is the universe expanding into, it's really difficult for humans to understand, because there isn't anything outside the universe. The universe is everything that there is. And so it's actually just space that's getting larger and larger. And it's very difficult to conceptualize. People also think about whether the universe has a center. When you think about the Big Bang, you think that there must be a central point, but that's not the case. So every single point in the universe was at the Big Bang. And that's really hard to conceptualize. But where's the energy coming from to cause this expansion, this accelerating expansion? That's what scientists call dark energy. It's not really a great name because we don't know what dark energy is. There's a number of theories, and that's why we've got these great experiments that are happening right now. So the Euclid Space Telescope that launched in June or July last year, and then there's the Nancy Grace Roman Space Telescope, one of NASA's next flagships, which will launch in 2027. And then there's also a ground-based telescope, the Vera Rubin Observatory, that will begin observing, I think, later this year or next year. And all of these missions are investigating dark energy and trying to understand what exactly is dark energy and how is it causing the accelerating expansion of the universe.
Great. That's so interesting. Euclid, let me just go to some practical questions about Euclid, and then we'll get back into the things that are a little more mind-expanding as well, or try to be. Euclid was approved back in 2012. Eventually, it was built and launched from Cape Canaveral on a Falcon 9 rocket, and that was last July 1st, 2023, which is wonderful that all this science is so contemporaneous. It's right now this is happening. And it was launched by the European Space Agency, ESA, I guess we can call it, in conjunction with NASA. Can you tell us about the partnership between NASA and ESA and what roles both groups play in making this all come together, the Euclid?
Sure. So ESA is the prime space agency, the European Space Agency, that decided to do Euclid in 2012. But that was after 7 or 8 years of lobbying and developing by scientists from primarily Europe, but some of us, including me, also from the US. And at that time, in 2012, the European Space Agency envisioned what eventually became Euclid with two instruments. One, a visible camera that takes pictures in light like we would see with our eyes, but the other camera, an infrared camera that takes infrared or heat vision pictures. And the best infrared detectors in the world typically come from the US, and so ESA approached NASA and said, hey, we'd like to partner with you if you provide these infrared detectors and the associated electronics to run those detectors. We'll build the camera and we'll allow a number of US scientists to be part of our science team that's going to use this Euclid data. So NASA and ESA entered a partnership where NASA was providing these detectors and associated electronics. NASA eventually also signed up to help process and serve the Euclid data to the astronomical community. That is, to do some of the data processing that takes those raw images and makes them useful for astronomers to use. And NASA is also funding a number of scientists in the US to participate in the exciting Euclid science that's just starting to come out now.
Fantastic. It's such an interesting project. Okay, this is going to be the easiest question I ask. It is, the project is named after Euclid of Alexandria, who lived around 300 BC and is considered the father of geometry. Why is it named after the father of geometry?
So one of the things that Euclid is going to be looking at is the geometry of the universe and understanding the shape of the universe. And so because Euclid was considered the father of geometry, it was a really natural name for this mission. Do you want us to add anything?
Yeah, I can add something to that, a little anecdote that I like to think about. So measuring dark energy is hard because its effects are very subtle. So we really have to measure the shapes or positions of billions of galaxies. So it's very challenging. And there's a story about Euclid that's probably, Euclid the person, that's probably not true, but I really like the story. The king at the time was being tutored in geometry by Euclid, the father of geometry. And the king came to Euclid and said, I'd really like some way to learn this more easily. It's very difficult to learn it. And Euclid is famously has said there's no royal road to geometry. There's no easy way. You just have to do the work. You have to study. So even the king didn't have a shortcut to learning geometry. And I like the parallel that there's no shortcuts to understanding dark energy. We have to do the difficult, challenging missions like Euclid and Rubin and make the measurements of billions of galaxies to understand the very subtle effects of dark energy. So there's no royal road to geometry, and there's no royal road for an easy way to understanding the contents of the universe.
That's great. Thank you. That's really great. Euclid is a medium class ESA mission. You guys call it ESA too, right? Everybody
Yes.
calls it ESA, or do you have to? Okay, good. ESA mission to investigate the expansion of our universe over the past 10 billion years, from before the expansion started to accelerate all the way to the present. And in other words, then, Euclid's mission is to better understand dark energy and dark matter by accurately measuring the accelerating expansion of the universe. So now we're going to get to the hard question, which is, how are you going to do that?
So one of the ways that Euclid is trying to understand the accelerating expansion of the universe is by looking at a phenomenon called gravitational lensing. And so what gravitational lensing is as light is traveling through the universe, it is being deflected by the galaxies and the mass in the universe. And what these deflections do is they change the shape that we see of the light. And so if you imagine that a distant galaxy looks like a circle on the sky, as the light from that galaxy is traveling towards us on the Earth, it's going past a number of big clusters of galaxies, and the shape of that galaxy might appear to be a tiny, tiny little bit more elliptical. And so we're trying to measure the shape changes of these galaxies, which is giving us information about the kinds of mass that is in between us and that distant galaxy, which is telling us about the evolution of the universe. And that all sounds really simple, but we don't know what shape the galaxy was exactly when it started, because galaxies aren't perfect circles or spheres on the sky. And the effects are also really subtle in most of the galaxies. So you may have seen beautiful images of these giant arcs, and that's called strong gravitational lensing. But that only happens in certain areas of the sky where there's very, very large masses. But what happens across the range of the sky is a very, very subtle change. We're talking about a 1% shape change on something that we didn't know the shape of originally. And so how we are doing this is we're measuring millions and billions of galaxies, and we're looking for a coherent shape change over a space. And so that's why Euclid is such a fantastically impressive mission, because it's going to be looking at more galaxies than any other mission has ever looked at, to measure those very, very subtle shape changes and understand what's going on with the evolution of mass in the universe from the very, very distant universe right back toward ourselves. Would you like to add anything?
So Euclid is going to use two techniques to study dark energy. And one is the weak gravitational lensing that Alina just described. The other technique is looking at the clustering of galaxies, how close galaxies are to each other. And there's imprinted on the universe at a very early stage of the universe's development is a preferred distance between two galaxies. So the distance between galaxies can be any number, but there's a preferred number where we find more galaxies at that distance from each other. And that distance, that preferred distance between galaxies, grows in time as the universe grows. So by looking at the clustering of galaxies, or how close galaxies are to each other at various stages in the history of the universe, we can see how the universe has grown or expanded over cosmic time. And in that way, we can reconstruct the expansion history of the universe and show that that expansion is getting faster and faster over time.
Great. Interesting. Really interesting. You're answering questions I haven't even asked yet, so it's fantastic. It's really good. Is Euclid attempting to detect dark matter, a little aside here, in our own Milky Way galaxy? And if so, what are you doing to accomplish that?
So Euclid's survey is designed to look at distant galaxies and look for these subtle, weak gravitational lensing caused shape changes in those galaxies. And so to do that, we actually look away from the Milky Way, because the stars in our own Milky Way galaxy get in the way of seeing those distant galaxies. So the design of Euclid's survey is to, as much as possible, look away from the Milky Way. And so we won't be trying to find dark matter in the Milky Way galaxy. And in fact, that would be a distraction from Euclid's primary goal of finding dark matter out in the distant universe.
Thanks. That's good. That's great to know. There are lots of hypotheses about what dark energy is out there. I don't know that I have the most current, but I've got three of them. Maybe they're long old news, and maybe there's something even fresher that you can tell us about. The first one that I read about is called the cosmological constant, and it says if the vacuum of empty space has an inherent energy, it may push the universe to expand. The strength of such an energy would be constant through time and would act just like the cosmological constant that Albert Einstein added to, and then he later removed, but added to his equation for general relativity. So that's one. Is that a hypothesis that still holds water, or has that been dismissed?
I'll start. So scientists currently believe that the cosmological constant is the most likely scenario for the universe. So that the dark energy is constant over time and it's causing this accelerating expansion. And as you mentioned, Einstein had this cosmological constant in his equations of general relativity. And so what the cosmological constant did when Einstein originally included it in his equations was it held the universe in a static state, because that's what scientists thought was the most attractive, aesthetically pleasing state for the universe. They didn't think that it was collapsing. They didn't think that it was expanding. They just thought that it was static. Now, when Edwin Hubble noticed that the galaxies that he was looking at through the telescope at Mount Wilson in the 1920s, that they were all moving away from us, no matter which direction he looked in, that's when he realized that the universe was expanding. And so scientists then thought that because of the Big Bang, that the universe would expand and then it would collapse down on itself again, and you didn't need a cosmological constant to hold the universe up in Einstein's equations in this case. And so Einstein saw this as the biggest blunder of his career, and he took the cosmological constant out of his equations. But then in 1998, when two separate groups of scientists were studying supernovae, they discovered that the universe wasn't just expanding, but it was also accelerating in its expansion. And lo and behold, in order for Einstein's equations to be balanced and to have an accelerating expansion of the universe, the way that you do this is by adding Einstein's cosmological constant back into those equations. And so what Einstein saw as the biggest blunder of his career actually ended up winning these two groups of scientists the Nobel Prize in Physics. And so it was a fantastic prediction of Einstein's. He just didn't quite have the mechanics of how it worked at the time.
I'm so glad you came up with that answer, because I was wondering why he had taken it out. I had read that and then put it back in. And so you certainly beat me to it, and that's a great explanation. There was another, just to test a couple other hypotheses that are out there. Quintessence, the idea that it's that dark energy comes from a field, like a field of electricity, an electric field or something, that fills the cosmos. Its strength could change over time, either increasing to eventually rip all structures in space apart, or decreasing and exchanging directions to allow the universe to contract in a big crunch. This is a pretty dark look at the future, but does anybody still think this is accurate, or do some people think that's still a viable concept?
So you're describing another possible theoretical explanation for dark energy. And right now, our measurements of dark energy don't have sufficient precision to rule out a number of different theories. The one that Alina talked about, the cosmological constant, that's sort of the simplest one in terms of the equations and our current understanding of the universe. And we don't have any evidence that it's not this cosmological constant, that it's one of these other theories. However, we don't have a good reason why the universe would have this cosmological constant. And if we look at other aspects of the universe, it's a bit perplexing why this very interesting property of the universe should exist. And so other theories like quintessence have other explanations that are a bit more complex in their theoretical explanation, but still aren't ruled out by any of the data. And so getting better data, more galaxy shapes, more galaxy positions, more exploding stars further back in the universe is what we need to distinguish between all these different theoretical models of what dark energy is. And that's what we're going to do, well, we are doing now with Euclid, and we will be doing with Roman and Rubin and other telescopes in the future.
And so if I can
I
add,
read that.
sorry,
Please do, yeah.
If I can add, so with some of these different models, if dark energy is a little bit stronger than we currently think, then what could happen is that the universe is not just accelerating expansion, but that things start to pull apart. So in the current scenario with the cosmological constant, the universe will become a very lonely place because eventually galaxies will be so far distant from each other that we won't be able to see other galaxies, and so it'll be very, very lonely. But if the universe, if dark energy was a little bit stronger than it currently is, that we currently believe, then what could happen is that galaxies start to rip apart, and then also the planets and within the galaxies and the stars within the galaxies start to rip apart, and then it could end up in what scientists call the big rip, which is where even atoms begin to rip apart at the very end of the universe. So these aren't the most favoured models, and we don't necessarily believe that that's what's going to happen, but these experiments that we're doing, like with Euclid and the Nancy Grace Roman Space Telescope, will tell us if we can rule out some of those theories.
Yeah, and I read that, and so I'm glad you talked about it, that cosmology is becoming more and more precise, more precision-oriented, and it seems that that's what Euclid is and where you're going with all these other telescopes. There was one last theory, which I want to bring up only because it relates to your Alina, your description of the ginormous size of the universe, and that is there is no dark energy theory, which is dark energy may not exist at all, and the acceleration of the universe expansion may instead indicate that gravity operates differently than we think on extremely large scales, which by all accounts this is a very large scale we're looking at.
So now you're talking about a modification to Einstein's theory of general relativity, our explanation of gravity, which has withstood over 100 years of increasingly complex tests. But that doesn't mean it's the correct or final theory of gravity. It just means it explains what we've seen so far. But there could be models of modifying that gravity theory that explain the observations we're seeing of the universe. So one of the really interesting things that Euclid and these other telescopes are going to do is they're going to use multiple probes to study dark energy or modified gravity. And in the case of Euclid, we talked about the clustering of galaxies and the weak gravitational lensing. And in some dark energy theories, those will behave one way, and in the modified gravity theories, those will behave in different ways. That is, we can tell the difference between dark energy and modified gravity because they have different effects on the weak gravitational lensing than they have on the clustering of galaxies. So that's why Euclid has to use these two distinct probes of the universe, the clustering of galaxies and the weak lensing, because that was what will allow us to distinguish between various dark energy and modified gravity theories.
Fantastic. Let me get back to some practical things. Euclid was launched 9 months ago. Can you tell us where Euclid is now parked?
So Euclid launched from Florida on July 1st last year, 2023, and it made its way out to what we call the Lagrange point 2. And so this is a point between the Earth and the Sun that sort of balances the gravity. And it's not a single point, it's about 1 million kilometers across. So it's a very, very large area. And Euclid is orbiting within this Lagrange point where it's sort of in a stable thermal environment and a stable gravity environment in between the Earth and the Sun.
This may be one of my many silly questions today, but if dark energy and dark matter make up 95.1%, I think it is, of everything, why did we have to go 1 million miles away to the Lagrange point to study it? Couldn't it be done closer or in another place? Or is that place with that halo orbit so perfect, and that's why why Euclid is there and why Gaia is there and why JWST is there? So.
Okay, so why do we put a telescope at this L2 or Lagrange point 2? So telescopes like the Hubble Space Telescope, which has been the most fantastic telescope in my view ever flown over the course of its lifetime, it's in the low Earth orbit. That means it goes around the Earth every 90 minutes. So every 90 minutes it's going into the sunlight, out of the sunlight, and that's causing it to thermally expand and contract. And it also means about half of the time the Earth is blocking any part of the sky that you might want to be looking at. So it's not super efficient to be in low Earth orbit. So if we send a telescope out to this Lagrange point 2, the telescope is not going in and out of the sun every 90 minutes. So as Alina said, it's a very thermally stable environment. So the telescope is very stable, and there aren't subtle changes in the telescope that might mimic some of the things that we're trying to measure in the galaxies. That is, subtle changes in the telescope can cause the measured shape of a galaxy to change, and we don't want that. So going to L2 gives us this thermally stable environment. It also is a stable environment in terms of where we can look on the sky. We're not going around the Earth, so the Earth isn't blocking parts of the sky, so we can look at much of the sky at any one time, and that allows us to do a very efficient survey of big portions of the sky. Now, L2 is further away than the moon, but it's not so far away that it's really difficult for us to send the data back to the Earth. So that's another concern, is that L2 is close enough that we can easily send all this data back to the Earth so that astronomers here on the ground can analyze it and search for evidence of dark energy.
Great. I read that ESA plans to find dark energy and dark matter by looking at stars as they were being born, like in the Horsehead Nebula. It's what comes to mind because we did a presentation on JWST when it first came out, and that was one of the images that we saw and talked about how that was sort of a nursery for stars. If that's accurate, and is there potential because JWST and Euclid and Gaia are all in the same orbit there, is there any possibility for overlapping, complementary work between the two of those, particularly JWST and Euclid, in using their different equipment out there in that same area?
So there's going to be incredible complementarity between the 6-meter JWST, I'm talking about the size of the telescope mirror, and the 1.5-meter Euclid. And the reason there's this complementarity is that they're doing very different things. So Euclid is going to look over the course of 6 years at fully 1/3 of the sky. And it's going to take images and of all the galaxies and everything we see in that full third of the sky. And in doing so, it's going to find a number of very rare objects that you have to look in huge areas to find. Now, the JWST has a much smaller field of view. It can only look at a very, very tiny piece of the sky, but it can look much deeper. So what you do is you find these rare or interesting objects with Euclid, and you say, yeah, I want to study that in more detail because I don't fully understand that object. And then you feed the coordinates of that object into JWST, and you go study it in much greater detail and much greater depth. So Euclid is going to be a fantastic finder of rare and interesting objects for JWST to follow up on later.
And so while
that's a great answer to the question. Keep going, Alina. Keep going. If you have more to add, please.
While Euclid has this great complementarity with JWST with its smaller field of view, it's also going to have fantastic complementarity with NASA's Nancy Grace Roman Space Telescope and also with the ground-based Vera Rubin Observatory. And all three of those missions are going to be investigating dark energy and dark matter over a wide area. But what we'll be able to do with all three of these data sets is we'll be able to use them together to get the tightest constraints possible on dark matter and dark energy and understanding the overall evolution of our universe. And so the Vera Rubin Observatory on the ground is going to be looking at the widest area of sky, and it's going to have an enormous data set over 10 years, really looking very, very deeply at the sky over time. And the downside of the Vera Rubin Observatory is that it's having to look through the atmosphere because it's on the ground. And then we've got Euclid, which is going to be looking at a wide area of sky from space. And so we can use these space images and compare them with the ground images to try to remove some of the systematics, the errors that the atmosphere introduces, and so we can understand the data better. And then with the Nancy Grace Roman Space Telescope, we'll be looking deeper than what Euclid is looking, but not in such a wide area. So again, we get to understand the data better by combining all three of these data sets, which will give us the most phenomenal understanding of what's going on in the universe.
That's such a great answer. One of the board members asked me to ask why we keep building so many different telescopes and sending them out. What's the point of that? Well, there is the point of it, that they're all complementing
Did you want to add anything to that?
To the other.
No, I think that's a great answer.
These are obviously very precise tools that were in the payload, all the cameras, the viz and the spectrometer and the photometer. How do you manage that from being biased, the information you're getting in there, from being biased by the machines themselves? And I ask that because in a video I was watching of a NASA video of the guys putting together one of the cameras, the cameras, he was talking about a dust particle on one of the 16 million pixels in the VIS instrument would completely make it impossible to see maybe a galaxy or maybe a planet or something you were looking for outside there, and it was a bit of dust. And so you're on a 6-year mission out there, and that's a possibility. What's the regime for calibration and recalibration on these things, just to make sure that they're not self-biasing them because of something?
Excuse me. All right, I can take that one. So Euclid's primary survey is surveying about a third of the sky, a very, very wide survey. But for a much smaller area of the sky, Euclid is going to do what we call a deep survey. And what we do there is we go back to this same area of the sky over and over, about 40 times in Euclid's survey. And so by doing this 40 times, we can look at any changes that happen in the camera. We get multiple measurements of the same stars and galaxies, and we can compare and see if there's any changes to the telescope or camera that are causing some of these biases. We also look at a few smaller fields that are very well studied from Hubble, JWST, and ground-based telescopes, and we compare the Euclid data on these very well-known and very well-studied fields to see if there's any differences in what we're measuring with Euclid versus these other telescopes. And if there are differences, it tells us that maybe we don't fully understand how one or the other telescope responds to the same stimulus from a star or galaxy. So it's by doing these repeated observations and observations of known objects that we can really calibrate Euclid's cameras very, very accurately.
Besides the complexity of the equipment, which is very impressive, the number of people who are involved in this is quite impressive too. I think there are more than 1,200 people in over 100 laboratories in 18 countries that will be analyzing this data, and that's impressive in itself. And considering the multiple countries that are involved and the languages that are involved and the teams and the individuals that are involved, how do you share the developments as they happen so that it isn't old news by after lunch, it's new news? How do you all talk to one another about what the day-to-day processes are?
So working in a large collaboration is definitely a challenge, but scientists have pretty universally agreed that the language that we will all use is English, which is lucky for me because I don't speak any other languages. So whenever we're communicating, we're all speaking in English, and we have the benefit of the internet, the World Wide Web, to send data and to communicate with each other really rapidly and to understand things. And one of the benefits of having this enormous collaboration of people on Euclid is that any findings that we make that might be slightly different to what we were expecting. We want several different groups to do that analysis independently to confirm the result. Because in science, we don't want to make a claim before we're really confident that we've got the right answer. And so we're really lucky in Euclid with so many different people that we're able to do the analysis in a number of different independent ways and make comparisons to make sure that no mistakes were made, so that when we communicate with the world about these incredibly exciting, potentially Nobel Prize winning results, we're very confident that those results are accurate. You want to add anything?
No, that's great.
Let me ask you about 3D mapping. That was mentioned, and I also don't quite understand how they do that. How does that work? How do they do 3D?
All right, so when we talk about three-dimensional mapping, we're using this gravitational lensing technique to map out where the dark matter is. And when we look at further galaxies away from us, we're looking further back in time because light has a finite speed, and it takes time for light to get to us. So if we look at a very distant galaxy, that might have been a picture of that galaxy 10 billion years ago, and a nearby galaxy might be a picture of that galaxy only millions of years ago. So by looking at how the dark matter distribution has changed over cosmic time from now, or millions of years ago, which is just an instant in cosmic history, to 10 billion years ago, we're able to make a three-dimensional map where the 2 dimensions is the sky and the 3rd dimension is outward or over time. And it's looking at the evolution of that 3-dimensional map that tells us about the properties of dark energy.
Got it. That makes sense. You're going to be, I'm trying to cut ahead of time because I have so much more to ask you here, and I don't know how I'm going to get to it all. So I'm just trying to, in my mind, cut a little bit ahead. Well, we know that about 10 billion astronomical sources will be observed by Euclid, of which 1 billion will be used for weak lensing to measure gravitational shear, and Euclid will measure spectroscopic redshifts for at least 30 million objects to study galaxy clustering. Because our audience is such a diverse group of people, I thought I would play my role as the sort of Greek chorus, the dummy in the room, and ask some silly questions. But it would be useful, I think, because a lot of the people who come to us will also then do studies, follow-up study. And so could you just run through, we've already gone through several different things that would be in the glossary for this, but could you just give me we've talked weak gravitational lensing. Could you talk about, and redshift? Did we talk about redshift?
No, I don't think so.
I think that we intentionally didn't use that word.
Oh, why?
You can explain. Why don't you explain redshift?
Redshift. So when we're talking about looking into the distant universe and looking back in time, the way that we measure sort of how far away something is with redshift. And what this means is as light is traveling through the universe, it changes its spectrum the further away it is. And so the redder the light is, the further away it is from us. And so when that light came out of this distant object, it was in a normal, so I'm not explaining this well at all.
I can take it if you want.
Yeah, I think you probably should, because I'm not explaining it well.
All right, okay. So the redshift is due to the expansion of the universe. And so the further away something is, the further away a galaxy is, the faster it's moving away from us. And when something's moving away from us, the wavelength of the light we see from that is spread out and becomes longer. And longer wavelengths mean redder light. So for any distant object, the light that we see is shifted towards the red end of the spectrum from what was emitted from the object. And by looking at how much that shift in the red, or redshift, there is, we can tell how far away that object is.
And so an analogy that we can use here on the Earth is when you have an ambulance that is approaching you, the pitch of the sound is higher as it's approaching you, and then as it goes away from you, it becomes lower. And that's sort of similar because the sound waves are being compressed and then expanded as it goes past you. So it's a similar phenomena except with light.
That's a great explanation. That makes a lot of sense. I know you've been working on N-body simulations, Alina, for a while. Is that something you can describe in a quick couple sentences?
So cosmologists use simulations to try to understand what's going on in the universe in preparation for these upcoming missions, because most of the stuff in the universe is this dark matter, and dark matter only interacts gravitationally. It's actually quite easy to make these big simulations. What we do is we use little particles that we call dark matter, and we plug in the equations of how they interact gravitationally, and then we run it over time to see what happens with the evolution of the structures over time. And we can use these to compare eventually with the observations that are coming in to understand what's going on in the universe and the equations and models that we're using and how accurate they are. And so it really helps us to understand what's going on through simulation, because we can do all different types of models of the universe in simulations.
I'm going to ask you, I've got a few more, but I'm going to ask you just one more. Baryon acoustic oscillations. Can you describe that? Because I think people are going to run into that when they start studying what Euclid is doing.
So baryon acoustic oscillations is a very fancy way of saying galaxy clustering. And that's what I talked about earlier, about one of the techniques that we'll use with Euclid or Rubin to measure the expansion of the universe, looking at how galaxies are clustered. And where this comes from, baryons are normal matter, not the dark matter, and acoustic means sound waves. Acoustic is sound. So very early in the universe, there were sound waves because the universe was so dense that sound could essentially travel through the universe. And there was a time in the universe when those sound waves got frozen into place. And there was a preferred wavelength for that sound. And that preferred wavelength is the preferred distance between two particles in the early universe. And those particles grew over time to become the galaxies we see today. So that wavelength of acoustic oscillations or sound waves that got imprinted on the universe in the very early universe is still observable today by looking at the distances between galaxies. We can see a preferred distance between galaxies. So we call that preferred distance between galaxies baryon acoustic oscillations. So it's a big way of saying the clustering of galaxies.
Got it. Excellent. I'm going to skip ahead because we're going to run out of time and just gather up a little bit more information here. Like, once data is collected and analyzed, how long will it be before it's shared with the rest of the world? I'm sure everybody wants to know what this is, what the Euclid is finding out there and how they can use it themselves. There are space agencies everywhere. So how long do you think it's going to take before this will be shared with everyone?
So Euclid took a number of what we call early release observations of known astronomical targets, including the Horsehead Nebula, which you mentioned earlier. And those observations are going to be shared with the world. That is, the data from those observations is going to be shared with the world in just 2 months, in May of 2024. Then Euclid will release to the world about 50 square degrees of the sky, and that is going to be released in probably March of 2025, so a year from now. And then about a year after that, or a bit more than a year after that, so early summer 2026, Euclid will release about 2,000 square degrees of coverage of the sky, or about 1/20th of the whole sky will be released at these really high resolution images and spectra that Euclid's going to be taking. So that's going to be the first really big data release just over 2 years from now. And I think that's going to be an exciting time, not just for people studying dark matter and dark energy, but that data is going to be really useful for a number of other studies of stars, galaxies, and all of these different astronomical phenomena. The Euclid data is going to be just a treasure trove of data for them.
And you should share, Jason, the comparison of size of these releases with, like, for example, Hubble and the amount of data that Hubble has released.
So over its 30-some year lifetime, Hubble has probably taken images of about 50 square degrees of the sky, and that's the area that Hubble has covered on the sky. And as I said, that's going to be the area of the first release of survey data from Euclid about a year from now. And that survey data that Euclid is going to release a year from now, that's already much less than Euclid has covered in its 1 month of operations starting about a month ago.
Is there any sort of practical private application for the work that you guys are doing?
So the Euclid data, that is the data of the distant universe, I don't see practical commercial uses for that. But developing the tools we use to take the data, that is the telescope and the detectors, both the visible and infrared detectors, there's a lot of practical applications, both in space, looking or observing the Earth, for instance, with these types of instruments, and on the ground. Everyone has a telephone with a very big camera, and those cameras have been developed in part with the space industry that's developing cameras and larger and larger format pixel cameras for use in telescopes. But the techniques that we're using to analyze the data, especially techniques in machine learning and artificial intelligence, those have a lot of applications across a really wide swath of what humans need. And the reason we need to use these machine learning or artificial intelligence techniques is because in the past, a survey of galaxies might look at dozens or hundreds or even thousands of galaxies, and you could imagine for that a scientist looking at each galaxy very closely for some amount of time on their computer screen or a printout or something like that. But Euclid's going to look at 2 billion galaxies for gravitational lensing, and many more billions of galaxies that we don't even use the gravitational lensing on. So for these billions of galaxies, there's just too many to look at them one by one. So we're developing techniques to have the machines and the computers learn how we analyze these galaxies and then do it for us. And understanding how those techniques work is going to be incredibly helpful for a wide range of other human endeavors. So a lot of astronomers go on to use those techniques in other areas of science or commerce.
Fantastic. Can you just talk to us for just a brief period about your Euclid team? You have 75 or 85, I think it is, members that have been sourced from colleges and universities all over America. Some really obviously very bright people have come. What is your org chart? How do their jobs come into play, and how are they differentiated? And then ultimately, do other countries in the ESA orbit, do they also have teams like this? And then how do you all communicate with each other?
So each of the countries within Euclid, that's the ESA countries, the European countries, as well as Canada, Japan, and the US, who are also partners in Euclid, have some funding structure in place to fund the scientists to work together on Euclid. So in the case of the US, about 12 or 13 years ago, I wrote a proposal to NASA and said, here is what I think you should spend your funding on with Euclid. I have a vision for how this would work. I have a vision for how this would evolve over time. And I put together a steering committee of preeminent scientists on my team that would help me make decisions for who gets the funding from NASA on my team every year. And now I get funding that goes to, at some level, as you said, about 80 people all over the US that are doing some work for Euclid. But I'm deciding who's getting funding, but they're all incorporated into this larger Euclid consortium, which is largely European, but of course contains a number of Americans, Canadians, and Japanese as well. And so we're all working together in this large structure to make the Euclid science happen. And this large structure has 14 distinct science working groups in different science areas. One is the weak gravitational lensing we talked about. Another is the galaxy clustering that we talked about. But there's also a science working group that's looking at planets, because while Euclid is not optimized or trying to look for planets, we will find evidence for some planets, and we want some scientists looking at the data to do that. And there's a science working group that's looking at stars. So my team in the US is mostly focused on the weak lensing, the theory, and the galaxy clustering, because that's the primary science of Euclid that NASA wanted to fund.
Interesting. It's so interesting. It's so complicated. It's the effort you're making it's a complicated subject, but the way it's being done is complicated and difficult and very impressive as well. Can you talk to us about the decadal surveys, the idea that you look ahead 10 years and decide, is this going to be old news by the time we start this project, by the time we get funding and all of that sort of stuff? And a little bit about what it takes, and you did already, a little bit about what it takes to convince NASA to fund and greenlight a new mission, with funding, of course, being important in everything.
So here in the US, every 10 years, scientists get together to think about and prioritize what are the main scientific priorities for the coming decade. And we think about things that go beyond the scientific priorities. We think about the health of astronomy and astrophysics in the US in general. And so the last astrophysics decadal survey happened in 2020. And the way that it was structured, the big funding agencies in the US, so NASA, the Department of Energy, and the National Science Foundation, charged the National Academies of Science to bring together a large cohort of scientists to think about these things. And there were a number of different panels that looked into very specific things. So there was panels that were looking into specific science areas, in addition to panels that were focused on different wavelength ranges and mission types. And I was on a panel that was thinking about the infrastructure for astrophysics across the US. And we all wrote individual reports that were then passed along to a steering committee for the final report and the final prioritization that takes into account the funding profile that we think that we're going to have over the coming decade. And that astrophysics decadal survey is the primary document that the community uses to communicate with the government and Congress in the US to encourage them to fund and support the activities that we're engaging in. And there's a number of different sizes of missions that we can do in astrophysics. And at NASA, we have these flagship missions, these very, very large missions that Nancy Grace Roman Space Telescope is actually one of. And Roman was prioritized in the 2010 Astrophysics Decadal Survey, and Congress ultimately agreed to support that, and NASA's now moving ahead with it, and it should launch in 2027. In the most recent Astrophysics Decadal Survey, the next big flagship that was recommended is called the Habitable Worlds Observatory, and as the name implies, this is an observatory that will be looking for exoplanets, that's planets outside of our solar system, that may host life. But this is also going to be an incredible facility for doing general astrophysics. So you can think like next generation Super Hubble. But there's also competed classes of missions that are smaller. And so these classes of missions were also recommended, and the centers that NASA centers are encouraged to put in proposals for these smaller classes of missions so that NASA has a very robust portfolio of missions across the wide range of wavelengths that we can look at.
It is astonishing how much NASA does that we don't know about. I know there are lots and lots of balloon, stratospheric balloon missions and things you had worked on in that arena as well before. Can I just ask you one quick question about, and then we're going to really have to move on, one quick question about politics. I can imagine that in your group of 100 different scientists working together, there's internal politics, and in that group with the other groups, there's internal politics. But in the other form of politics, funding, is there, after doing 20 years from the time you started in 2006, pitching this, selling this, getting this together, then it gets built, then it goes out into space, during that period, have you run into defunding by congressional or presidential mandate for any of these projects? Or is once they say yes, the money's there, you don't have to worry about it?
So for Euclid, since NASA is not the lead, the NASA investment in Euclid is small enough that it's NASA really making the decisions with the budget they have and not having to go to Congress to justify or get funding directly for Euclid. It's within NASA's discretion to fund that. And early on in trying to get NASA involved in Euclid, there was some stops and starts where NASA would move ahead and then say, oh, I'm not sure that we can do it. But once NASA committed in 2012 to doing Euclid, NASA has been an incredibly strong supporter of Euclid, my team, a good partner with the Europeans. So the NASA support for Euclid has been unwavering and really fantastic to see. Now for Roman, we've had a different story over the past 10 years. When Roman is large enough, it's one of these flagship missions where Congress has to say, yes, we do want to do Roman, and Congress sometimes move ahead, and then the administration, the president could say, well, I'm not sure that we want to do it. And then there's a debate at the highest levels, which of course, me as a NASA employee, I don't get involved in those. I just try to make the best scientific case for what I think is necessary. But ultimately, the Congress and the president's budget have supported Roman and continue to support Roman, such that we're looking at a launch just 3 or 4 years from now.
Fantastic. You know, it's you must be a very good salesman to have been able to go to them in Congress and say, you know, even though you're going to raise your hand, somebody in their town hall meeting and say, no, we need more. We have people on food stamps. Why are we spending money in space? You've managed to sell them on going to find something that nobody knows where it is, what it is exactly, but we should do it. And we're doing just amazingly big and valuable things with this particular project. Sadly, I would love to, I've got 20 more questions about the Nancy Grace Roman and all of these things that we've been talking about, but at least you've touched on all of them. And for that, I'm very, very appreciative. It's fantastic, and hopefully we'll be able to get you guys back in the future and as some of these other things unfold. Let me just ask you 2 quick questions. Can you speculate for us about what you think might be the most important discoveries that will come from Euclid about the nature of the universe? That's the big one. And then the second question is there a chance that Einstein's theory of relativity may be proven wrong by the work that's being done with Euclid now?
No, I'm going to go first, because then... So, the most important thing that I think is going to come out of Euclid is something that I am sure that I have not imagined yet. And I think that historically telescopes have really borne that out. That we start doing the observations with a very specific science case in mind, but ultimately the most exciting science that comes out of these missions are things that we didn't envision when we were preparing for them and when they launched. And I feel quite confident that Euclid is going to find many, many things that I haven't thought about that are going to be just so exciting, and I'm really looking forward to that. And of course, I'm very excited for the cosmology, and I think that science is going to be amazing. But I'm really looking forward to the things that we haven't thought of yet. And then
I'm so glad you answered that way, Alina, because I had read something about you talking about the romance that's involved in this kind of science. And it isn't just all facts, figures, and math. There's a sense of we're looking for knowledge's sake. And if it turns into something more than that, great. And if we even fail at it, that's great. So that's a great description. It's great. It's discovery, which is really exciting, really exciting. Yeah. Jason, what do you think is going to be the best thing out of this? And what about Einstein?
So I'm going to combine those 2 questions into one and tell you that Euclid and Roman are coming at a really exciting time in the history of cosmology. So we have really good measurements of the very early universe from, for instance, the Planck telescope from ESA, again with NASA as a partner. And we have some pretty good measurements from the ground of the more recent universe. And there's, we know what the physics that takes us from the early universe to the late, more recent universe is. That's Einstein's theory of relativity. But there's some emergent discrepancies between the early universe, which we've measured very well, the late universe, which we've measured reasonably well, and the physics that takes us there. And those discrepancies are becoming more pronounced over time. And with Euclid and Roman, we're going to make much, much better measurements of the late universe, that is the universe over the last half of the history of the universe. And if those discrepancies are still there when we make these much better measurements, it might mean that the physics that takes us from the early to the late universe is wrong, or perhaps more correctly put, is incomplete. So one of the most exciting prospects for me is that Einstein's theory of relativity is incomplete, and we need some new physics to describe how we go from the early universe to the late universe. And I think Euclid and Rubin will give us the data that we need to show whether that's needed for us to explain the universe. So there's a tantalizing chance that we're going to get some new physics that, I guess, transcends Einstein's theory of relativity that's going to be borne out by Euclid and Rubin. And for me, that's the most exciting thing.
These are very exciting times in which we live, and you guys are both very deeply engaged in it, and it's been a real pleasure to have you here to tell us what you're doing and where it's headed. And I know you're going to have a lot more people following the news about Euclid and what's going on at NASA after we get this word out about it too. And hopefully we'll have a chance to get you guys to come back here. I hope you'd be willing in the future to give us more details about some of these coming online projects.
Absolutely.
Thank you guys.
We'd love to.
Yeah, thank you for having us.
Great.
It's been such
Beautiful.
a privilege to be here with you.
Oh, it's been such a pleasure. Thank you guys so very, very much.
Thank you.
Thank you.
Thank you, Alina, and thank you, Jason. It's been fun getting to know you and learn about the remarkable and really challenging work that you and the folks do at NASA JPL and ESA, and it is truly inspirational. So thank you again for sharing it with us here today at the Forum. And thanks to all of you, wherever you may be in the world, for being with us today. If you'd like more information or updates about the Euclid mission and all things NASA related, go to jpl.nasa.gov/mission/Euclid. All of this should be on your screen. For additional links on the subject of today's presentation and for news about upcoming Forum programs, please visit our website at shforum.org. We'd like to thank the following people for their generosity in making the St. Helena Forum and its continuing programs possible.